Hello, everyone. Welcome to our brand new episode of Corecast. I'm your host, Tim.
I'm Mikey.
And this is Sahil. Welcome everybody to a brand new exciting episode of Quirtcast. Before we get started, if you haven't already, do join our Discord channel so you can ask us questions there. And then if you're joining from YouTube, ask us questions there as well so we can get to them during the episode and hopefully resolve any burning curiosities that you have. So without further ado, let's get to it. So one thing I was looking at and reading about was this concept of holography and holograms involved in the field of quantum gravity. I guess like that is a lot to unpack. So let's like first start off with like what is quantum gravity at like a high level, and then like dig further into it. So Tim, I'm gonna throw this question off to you. What the hell is quantum gravity?
Yeah, I think it's like a natural marriage, right? We know that our world is governed by quantum mechanics, so naturally gravity must be quantum mechanical in some ways. And the reason why there's such a like almost like quantum gravity is like a special word. It's like, oh, quantum particles, that's not so special. Particles are quantum mechanical. Like, what the heck? But like somehow quantum gravity, it's got like a special connotation. It's because traditionally, if you have watched like PBS documentary, whatever, The Elegant Universe, there's this lore that like gravity and quantum physics kind of don't mesh well together, right? So that's why and the reason mainly is because gravity, at least in Einstein's theory of gravity, generally the objects in those theories are very large, and quantum physics usually deals with things that are very small. So there were some questions, whether those two regimes, the large and the small, can be reconciled, and then we can have a quantum theory of gravity. Although it turns out that there is actually some difficulty with this reconciliation, and that's why the kind of the word quantum gravity becomes popular. It kind of becomes a big field of interest, subjects for research, because the idea is how can we make them compatible, and it's not obvious, right? So I would say that's roughly what quantum gravity is and kind of the context behind it.
I see. Where would you need to make them compatible? You mentioned like gravity, at least where Einstein was studying, it was very large, and quantum mechanics very small. So where in the universe do you see like the large and small coming together? Either Mikey or Tim, go for it.
Black holes.
Ah, good answer.
Yeah, right. Black holes are the most interesting playground for thinking about these kinds of things, because it's like a regime in which microscopic effects are important, but also purportedly the gravity is very strong in that region too. So this has always been kind of the playground for physicists to think about things like quantum gravity. And yes, Tim mentioned, for the longest time people didn't think that these two ideas could fit with each other, because the kind of basic framework in terms of the theory for gravity, which is Einstein's theory of general relativity, if you take the basic framework for thinking about microscopic objects, which is quantum mechanics, they don't paint the same picture of the universe. And if you actually put them together in a logically consistent way, they seem to be at odds with each other. But I don't know about you, Tim. I feel like this is purely a function of the fact that the theory of gravity, as you mentioned, is it's like an effective theory that works on long scales. And I think the smart money, most particle physicists would bet on the idea that the true theory of gravity, like we would consider Einstein's theory to be an approximation, but the true theory of gravity is something that has to play well with quantum mechanics. And due to a lack of imagination over the last 60 years, it's kind of seemed like this was a contradiction. But as I mentioned, I think this is purely just a lack of imagination.
Gotcha. That makes sense. I guess then, like, in their attempts to unify these two things together, what are some consequences that have come out of that were unexpected or like just surprising?
Yeah.
Or not so surprising actually.
Let me just add. Yeah. Let me just say, when you try to combine them, I think to me, I think one
in a naive way.
Huh? Yeah, I guess so. I guess first you can just try to just mishmash them together. Be like, hey, gravity and quantum, just get together, right? And then it turns out that the most sacred principles on both sides seems to kind of take a hit, right? So in a previous episode, we kind of mentioned what is the most sacred laws of physics, and from the perspective of quantum physics, that is the preservation of quantum information. It's the fact that all possibility must persist. You can convert one possibility to another, but they can never be deleted or cloned or copied in any way. They can never be expanded or deleted, right? And a technical note, this is called unitarity, right? Things are preserved. This possibility is preserved. But it turns out that gravity is it's a very effective machine for destroying, or at least attempt to destroy these information. And most notably, black hole is one of them. For example, if you throw something in a black hole, you can never retrieve that object. So that's just a basically, because not even light can escape, the black hole. So once you toss something in there, it's gone. So if you toss some of the possibilities of the universe or some of the wave functions in the universe, toss it in the black hole, well, shoot, it seems to be gone forever. So what happened to say with we mentioned the most sacred laws of physics, that this information cannot be destroyed or recreated. Like, that's a head-on collision right there.
You were saying, Mikey? I think you were going to say something. Or
no, I mean, not necessarily, but I mean, yeah, just to follow up with that, like, I feel like a lot of this comes from the fact that Einstein's theory is so beautiful. So because it's so beautiful, people think it must be the ultimate truth. They can't conceive of the possibility that Einstein's theory could just be an approximation to the actual truth. But like Tim mentioned, like it's very difficult to think about gravity on small scales. And so yeah, Einstein's theory is very beautiful when you paint the picture in large scales. Like mass causes a curvature of space and time, and things react to that. But what's actually going on at the microscopic level when these things happen? Einstein's theory doesn't really have much to say about that. And if you take its logical conclusion to its end, it doesn't really quite make sense how Einstein's theory could account for microscopic interactions.
I see. That does make sense. So what I'm hearing is that the naive approach of just kind of forcing them together in some very, I don't want to say like ad hoc way, but just very like.
It is ad hoc.
Oh, it is ad hoc.
Okay. It's completely ad hoc. Yes.
So basically, over the last 30 years, people have been trying to combine these theories in an ad hoc way, and the naysayers have been like, "Well, Einstein's theory is more beautiful to me." So yeah, there's a serious problem here.
I see. Okay, so if that's ruled out and that violates this preservation of quantum information, I think we called it unitarity as well back in our previous episode. Then what's left? Is that the end? Do we stop here, or has there been other approaches?
So I don't want to get into too much of the details yet, but this is sort of the whole debate between Stephen Hawking and many other physicists like
Lenny Susskind,
right, and many others that I'm discounting, right? But the ultimate, at least part of the resolution to that is that ultimately quantum information is not destroyed, and that's a consensus. So quantum physics prevails basically. And what emerges, I would say, is sort of a new idea, a brand new principle that we believe could be, at a similar footing in terms of sacredness to the conservation of quantum information. And I think that is called the holographic principle. And I think, Mikey, would you agree or disagree with me that this has emerged recently kind of as a new sacred principle, kind of?
It's hard to say how sacred it is. Yeah, I mean, it does seem.
I guess it can be derived, right? In some ways, in a logical sense, it can be sort of derived.
I think once the physics community understands it better, it could very well end up in one of those being called something sacred. But I mean, the way it arose was kind of like a surprise, right? It was almost like people just noticed this connection between these two different theories that were supposed to be incompatible, by the way. Like everybody says, Einstein's theory, quantum mechanics are incompatible, but hardworking physicists like Juan Maldacena noticed these parallels between the two theories and were able to draw these kind of lines between them. And I feel like that's kind of at least historically, the story of how
Yeah.
holography came into existence.
Yeah. Mhm.
Yeah. So I guess before we delve into that, what exactly it is, maybe we can talk about what a holograph is, because my notion of holograph is like back, I think, in like the older Star Wars movies of seeing like these holographic like aliens playing some kind of chess game with each other, and like I don't know, and like R2D2 projecting like I don't know, I think Princess Leia or something like that as a hologram, sending some message saying, "Help me! I'm in, I'm in trouble." So like, is that the hologram you're
Help me,
talking
Obi-Wan
about? Or...
Kenobi. You're my only hope.
Yeah. Yeah. So is that the hologram we're talking about, or like is this completely different?
I mean, yeah, that's exactly the kind of like. But so if we break down what it means, it's like what is a hologram? A hologram is a way of encoding information that could be surprising, right? Like you have a projection screen, and it encodes, I think the best way to think about it is like, I don't know, like a 3D movie these days, right? We can put on 3D glasses and see that there's like a three-dimensional encoding of the information, but what produces that information is a 2D piece of film, right? That 2D piece of film has some extra layers that are encoding information about 3 dimensions, so that when it projects, I look at it, and if I'm using the right kind of glasses, it looks 3D to me. So a hologram fundamentally is kind of a way of encoding more information than you thought could be encoded. Like you would think that if I just project a 2D screen, I see a 2D image, but there's ways of kind of layering the information so that when you take a 2D object, you can project it and actually give someone the sense that there's 3 dimensions going on.
Whoa. Wait. What?
Yeah, like a 3D movie, right? Like so, like a regular movie, right? You got a 2D film projects to a 2D screen, right? And even if you wear 3D glasses, you're still just going to see a 2D screen. But if you're very clever, and if you encode that information in a special way, you can take a 2D film, throw it on a screen, and if you put the right kind of glasses on, you'll see that there's like a 3-dimensional experience kind of encoded there. I think that's the basis of what holography is in general.
Yeah, but that seems really bizarre. I mean, like I mean, I'm speaking from everyday experience where like I have the notion that I'm moving through a 3-dimensional space, or like I have the sense that I can like move in 3 dimensions. So
Yeah.
what this like 3D to 2D business?
Have you seen a 3D movie, dude?
Well,
It's crazy. The snake comes at you, and it like feel like it's coming at you.
well. Let me just add that this is actually not as crazy as one would seem, right? Like, of course, if we think that, oh, we're 3-dimensional creatures and you can't just squash us on a 2D projector, like we're not being projected out of projector. But let's think a little broader, right? Like the universe is ultimately 3 plus 1 dimension, right? And you can ask the question, well, are we really fully utilizing the 3 plus 1 dimension? Like, for example, Sahil, you are pretty predictable, right? Like your body, your hands are, well, I mean, reasonably. Like, I wouldn't expect you to just travel.
As much as any other human is, let's say.
Yeah, as much as any other human is, right? So
not more predictable than your average.
not more or less predictable, right? So to some extent, I wouldn't expect you just like appear in Jupiter for no reason. Right?
True, yeah.
Yeah, so to some extent, the information I have, the 3-dimensional information I have for you at this 1 second is pretty good. So I can pretty much make a reasonable guess on what that next second is, right? So in this viewpoint, you're not really 3 plus 1 dimensional. You are just 3-dimensional. And then I can roughly kind of just predict what happens in the next second. And in that sense, I can say that you're kind of like a projection. Your future is kind of a projection of your present, right? And that's sort of part of the essence of the holographic principle, is that certain things you can predict from the boundary. You can predict from certain things, you can extrapolate inward. And I think that we do have some everyday experience of that, because things are not totally crazy and unpredictable in the universe.
That is fair. I guess like where I kind of want to like hone in on is the moving from three spatial to two spatial. Like what like how does that work? Because so much of what I've learned in like physics has been 3 plus 1 dimensional. And now we're saying I think 2 plus 1 dimensional. I'm not sure if the time component is there.
Yeah. So this is an excellent question, right? So going back to the analogy, if you accept the fact that, you know, like like when we live in a 3 plus 1 dimensional space and time, you can think of that as kind of like a projection from just 3 dimensional space, right?
Mm-hmm.
You know, how do we go from that scenario to a scenario where we only involve spaces? This is through relativity. Relativity, or general relativity, Einstein's theory, mixes space and time. So when time and spaces get scrambled, and you accept the fact that a 3 plus 1 dimensional thing is kind of sort of equivalent to a three-dimensional thing, then it's not so crazy to accept that 3 plus 1 dimensional thing might be equivalent to a 2 plus 1 dimensional thing. And an explicit example of that is just the surface of a black hole, going back to our example.
Can you expand that a little bit more for our audience that may not be familiar with this?
Yeah, so I guess one way to resolve this conundrum, going back to that example, of the fact that when things fall into the black hole, the information seems to be totally lost, right? The one proposal to fix that is that maybe the surface of the no return to event horizon, where things cannot return, because you cannot probe into the black hole, maybe that surface encodes the information of everything that has fallen in, right? In order for you, as a matter of fact, if you believe that quantum information is preserved, it's gotta be preserved somewhere. And like the only candidate pretty much is the surface of the black hole, right? So in a very real sense, that surface is a transformation of everything that has fallen in. It's literally like a squashing down of three-dimensional objects onto the two-dimensional surface, right? By gravity, like in a very physical sense. So that would be, you know, using the power of gravity, it kind of created a holographic screen.
Yeah, I mean, the way to think about it, like, so Sahil, imagine that we're all living in a box, right?
Mm-hmm.
And imagine that every single action that we make, every single breath we take, every single move we make, such thing, imagine that there's some reaction to that you can see on the surface of the box. You don't have to see what's going on inside of the box.
Mm-hmm.
Somehow just looking at the surface of the box is like a probe, an exact probe of what's going on inside the box. So if there's a person inside the box like jumping up and down, you'd see some pattern appearing on the surface of the box that would indicate exactly what the person is doing, right? It appears that something like this could be true for our universe. And as Tim mentioned, this has to do with gravity and quantum mechanics, but it's surprising, right? Like I'm not going to discount the fact that it's surprising, but if you take the laws of quantum mechanics and together with gravity, you kind of get this picture where this is inevitable, where whatever's going on inside the box has to be perfectly described by something on the surface. And as Tim mentioned, the biggest evidence for this is black holes. If this was not true, then the conservation of information would be nonsense.
I see. So kind of piggybacking off that, it seems like the examples we've used so far relate to black holes, which is a kind of more extreme example. But like, how can you say that, extrapolate that to the universe as a whole, whereas like all the examples you've given are black holes?
Yes. So we have to talk about black holes, I mean, because of the fact that that's where the paradox lies.
I see.
If quantum information can be destroyed, then nothing we're talking about has any merit. But as Tim mentioned, the conservation of quantum information is a very sacred principle. If you assume that has to be true, then it means that the surface of the black hole has to tell you what's going on the inside. And so it is restricted to black holes to a large extent, and this is, I guess, another leap of faith, but it's surprising the extent to which the shape of the universe kind of resembles the shape of the black hole. in terms of geometry. And so it's very easy for physicists to imagine that the same principle holds for the boundary of our universe.
Is there a way you can like high level state what the geometry of a black hole and the geometry of our universe are like the same? What do you mean by that?
But the fact that they both have horizons, so like our universe has a horizon because it's expanding and the rate of expansion is increasing. And so there's parts of the universe that we will never be able to interact with, in the same way that if you're inside of a black hole, there's certain things that you'll never be able to see because of the fact that it represents a boundary between which communication is possible. It's like a hard boundary. There's a similar hard boundary around a black hole in terms of an inability to communicate across it. A very similar boundary exists at the boundary of our universe, which we call what's it called?
Cosmic horizon?
The Hubble volume?
Yeah, the Hubble sphere. Yeah.
Yeah, I guess the point is that, it's not that we like to hound on black holes. It's just because that quantum gravity has a propensity of creating these boundaries, these borders where nothing can cross, right? But then the problem is, in order for quantum physics to preserve information, the information has to be able to travel. But if Einstein tells us that they have some limit, they have to travel at the speed of light, at some level, those information at some point has to be stuck on those surfaces. I think that's the crux, right?
Yeah. If you believe that the speed of light is a true speed limit, and if you believe that black holes exist in the way that Einstein thought of, then there are hard boundaries to what you can access and what you cannot. And the surface of the black hole in that sense is exactly the same as the boundary of our universe.
I see. So let me reiterate what you said to make sure I got it. So what you're saying is information needs to be preserved as one of the sacred laws of physics. So with the case of a black hole, this paradox arises, and if you want information preserved, then one solution to it is to have it plastered on the surface, which means you can basically tell all the stuff interior based on the surface. And so because the geometry of a black hole and our universe are similar with this whole horizon business, we also extrapolate this to the boundary of the universe, saying you can say kind of what's going on inside the universe, for lack of better words, through observing its boundary.
I would say that's exactly correct what you just said.
That's exactly. But
Good job.
Yeah, but I would say that there's a little bit more leap of faith here, right? Like, for example, who are we to judge that there's something special about the boundary to a black hole, right? Like, this is the leap of faith. If you believe that there's truly nothing special about the boundary of a black hole or the boundary of our universe, then you would say that every surface that you ever draw, that surface should, in principle, contain all the information inside that volume. Like, that is the leap of faith.
Yeah, how far do you want to take this? You can take it, I mean, it's logically reasonable to take it as far as Tim is saying.
So that is the full holographic principle. That would be the stronger version. It's like me. If I draw a volume around myself, like, that volume must be, in principle, be able to encode all my information.
Oh, I see. So I guess, like, does it become tricky because, like, if I look at from where I'm standing, I have a different, like, I don't know, Hubble sphere than you do slightly. So, like, what is the boundary of the universe that we're talking about here?
I think this is the tricky part because clearly researchers haven't hammered all that out yet, and because our universe, unfortunately, is a very complex universe. Every observer can have a slightly different boundary. So when we talk about us as a projection of the boundary, you're right that this is not very well defined. And this is one of the long-standing problems on how do we define the boundary. We know that
we're all very close to each other relative to the distance of the boundary.
So let me just say that physicists have looked at toy universes where there is an unambiguous boundary, right? And in those cases, it works. In those toy physical models, literally everything that you want to calculate inside the universe can be totally captured by what's going on the boundary. There's a mapping. There's a dictionary. You can say, like, hey, in that universe, Tim's having lunch. Well, on the boundary of that those toy universes, what does that look like? Well, that might look like some particles moving around in some other particular way, but there's an exact one-to-one correspondence. So that
We literally call it a dictionary.
yeah, a dictionary, right? But how to generalize those toy universes to this universe? That we don't know.
That's fair. That's fair. I guess like okay, so let's say I buy all these arguments. What is this at the end of the day? What does this tell us about the universe? What does it mean for us to be holograms, or like in terms of our humanity? Like, is there anything like any implications of that? Yeah, I'm just curious.
I think that's like totally up to the what is it, the eye of the observer. But to me, what it means is that like what I thought, like, oh, what's important is here now, like what I'm doing right now, like, you know, something horrible happened to me and I'm depressed because like what happened to me here now is so sad. But it kind of just spreads that out onto the cosmic boundary, and you realize that your existence is not really localized to here and now. It kind of gives each person a kind of cosmic extent in terms of their existence, and I don't know, that helps me sleep at night.
How about you, Tim? What implications does this have? Like,
Yeah.
why is this important? Is my question.
I mean,
Beyond-
these kind of questions, probably in the academic circle, other physicists will give me a lot of crap for answering it.
Yeah, they don't like to think about these things. 'Cause-
But at the end, I honestly think these are intriguing philosophical questions. Like, it tells you that, you know, if you think of yourself as a hologram, in a sense, you're kind of immortal because like, sure, I live this short life extent, but all the bits, quantum informational bits of me extend all the way to the beginning of the time and to the end of time. All the cosmic fluctuations, whatever, you know, long after the solar system dies, the sun goes, I don't even know, red giant engulfs everything, like way after like I no longer exist in this form anyway. But like that information is just forever preserving and also projected kind of all the way to the infinite past and the future. And yeah, that to me is kind of like the greatest notion of immortality, I think. Like, it's better than
I would
any
back that
religion.
up. It's definitely a notion of immortality. It means that our existence is not restricted to here and now, like dramatic people like to imagine.
Yeah, I would argue that this sort of viewpoint is better than, personal opinion, it's way better than what many religions offer, and it's like way more imaginative, or what's the word? I think let me put it this way. I think the way humans imagine immortality, like you go to some kind of human-centric, like,
narcissistic interpretation of immortality.
I think that's kind of, you know, it's kind of unimaginative, right? Like if I were to die, would I really care to live in like a human-like society again? You know, I would rather be part of this cosmic information flow of information, and will be like a way better experience, honestly.
It is a great experience. We're all experiencing it now, and it's great. And
maybe we'll coin it like this. What is this, like cosmic nihilism? Maybe it's better than that. Optimism, cosmic optimism.
Cosmic optimism. Yeah.
It
And by
of-
the way, I just also want to point out that I don't know, it has the undertones of like the simulation hypothesis, right?
You know, I don't subscribe to that, but
Yeah, but it doesn't say that we live in a simulation, but if we do live in a simulation, it kind of describes a natural interpretation of the coding language or whatever you want to call it.
I see. It for some reason this is reminding me of like, instead of like when you die planting yourself as a tree, you get planted as like a cosmic tree or
a cosmic hologram.
Cosmic hologram.
I'm waiting for my infinite future
The
to
boundary
be
of being-
projected to the boundary of the universe.
It's nice to plant yourself as a tree, but you will live on regardless of whether or not you do that. Like a
Yeah.
tree is like a symbolic way of encoding your material self, I think, in
Yeah.
something that will last longer. But even if you don't do that, you know, same effect.
Yeah, understandable. So from what I'm hearing, the takeaway here is that the concept of locality that we're all used to, the sense of like that we're very much localized here,
And
with
that this is so important. Here and now is so important.
yeah, is actually kind of bogus with this holographic principle. Is that correct?
I wouldn't say it's bogus because, like, I'm not trying to discount the fact that here and now can be important to a lot of people, but I think it shows that the importance of here and now is just one interpretation, and there is another interpretation in which you are immortal. And so, don't worry about that.
All right, all right, Mikey. I have a question for you, slightly more spiritual-esque, but
Mhm.
like the past and future is something that you can't access, and I've heard like being present is super important, the here and now. So how do you reconcile these two things?
Being present is super important, I think, for like, mental stability and things that are relevant for here and the now. Um, but it doesn't discount. It doesn't. Yeah, Hmm. I have to think about that one. I mean, obviously, you have to, be present in the here and now in order to lead a successful life. But I don't think you have to be worried in a cosmic sense of. I think a lot of the fear of death comes from like a worry that nothing matters, or
Mhm.
that like my actions don't matter. And I think that the holographic principle just demonstrates that to be patently false.
Oh, all right. So we're basically at almost at time. I want to leave you guys to give any last concluding thoughts that you have on this holographic principle.
Yeah, I want to just conclude that as a quick summary, right? When you combine quantum gravity and quantum mechanics, and if you insist on the preservation of quantum information, which I think many physicists would agree that it's super sacred, you are led to this holographic principle, and and by accepting that, you're rejecting this locality as a principle to be less sacred. You're basically saying that, hey, because the holographic principle is inherently non-local, right? So this is a not very obvious but super, revelation in modern science, and I think, and hopefully this gives the viewer more context on why the Horizon Telescope, if you haven't seen it, it's quite important because we're literally studying the surface of the black hole, and it could literally be a hologram. So stay tuned. We're making science breakthroughs, I think.
Anything you want to say, Mikey? Before we
Yeah,
head out?
to me, it reminds me of like one of my favorite stories about Einstein. So one of Einstein's best friends died, and Einstein, one of the famous, he wrote a letter to the wife of his deceased friend, and he said, "Do not be sad, because for us as physicists, we understand that the distinction between past, present, and future is merely what was it?
An illusion,
Uh,
or is that something else?
no, it was yeah, it was an illusion, but it was a uh, oh shoot, oh man, I'm gonna screw this up, but
Do I
it's
want to
it's like
search for
a
it?
it's like an unreasonably compelling illusion. And I feel like this, like, even though Einstein had a lot of things like, details about this story wrong, I think he understood the heart of it when he said that. And I don't know, that's the takeaway for me.
Very nice, very nice. I will ponder that when I'm thinking about the present. All right then. Well, on that note, I want to thank everybody for joining us, and we'll see you all next week.
See you all next week. Bye.